is interesting because other stats books don't have section 6.4 where it is. Other statistics books don't do that. They kind of wait. But your author said, well, wait a minute. I know that very soon we're going to be talking about estimating. Okay? And so I'm going to, in section 6.4, introduce this already. We already did some estimating. What was it that we estimated in section 6.4? We estimated the mean. We estimated the standard deviation. The variance. All right, so I'll put them together. Right? And then a proportion. That's the newest idea, right? P. The proportion of a population. Okay? So how do we estimate the mean? Well, we use X bar. What's that stand for? The sample mean. We may not know the mean of the population, but we can compute sample means, and that's what I did on the board with you. Remember that dot plot? And we may not know the variance, but we can compute a sample variance, and we can talk about how that works as an estimator. I'll tell you one thing. These we're not doing today. We're going to wait on these. Wait till next week. In some ways, there's something else we have to learn about before we get to that. And how do we estimate the population proportion? Well, we take a sample and look at the proportion in the sample. Okay, we call that p hat. So there's the notation that we learned in section 6.4, but they didn't really tell you clearly yet how to do it. I almost feel like after we get through today's lesson, maybe I won't even have to answer those questions, but I think I will. I think I'll go back. So we'll see. Okay. And you notice what we do is we're going to start with population proportions. So there's a reason that he introduced this right away. In some ways, this ends up working out the nicest. When you want to estimate the mean, well, there's a little more work involved. And we'll see that today and next time. But population proportion works pretty nicely. So let's go ahead and start that. Now, a couple of definitions. These are in the book, but I still want to take time on them. A point estimate. The important thing here is that it's a single value used to approximate a population parameter. Everything I just put on the last screen, in other words, when I put X bar next to mu, right? These are all point estimates. They're point estimates of a parameter. Right? So if you take the numbers 0 through 9, and you wanted to find the mean of the numbers 0 through 9, well, we could add them all up. 1 and 9, 2 and 8, 3 and 7, 4 and 6, right? And divide, and I think we get a mean of 5. All right, or 4 and a half. Let me do it. If you throw the 0 in there, you get the 4 and a half. Okay, so we get a mean of 4 and a half. But when we took point estimates, right? That was when we just took our 4 digits, a sample, and we computed the mean. Those means were all over the place. And we actually graphed them, and as we started to graph them, they started to look more and more like a bell curve, like a normal distribution. Okay? So these are point estimates. And, you know, will this be exactly the same as mu? Probably not. But if you graph lots of point estimates, if you graph lots of X bars, they look like that, and they're going to be centered on the mean. Okay? If you graph lots of X bars, that's what we learned about estimating the mean last time. Now here's a nice fact. The sample proportion, which we denote by p hat, is the best point estimate of the population proportion p. Now I have to tell you, your book does not tell you how they know this fact. Okay? They don't. This was proven by, well, mathematicians and statisticians. If you take a math major course, you'd study this, all right? What your book does tell you, although it's very kind of short, is they do tell you what they mean by best. That's what I want to talk about. Okay. I guess to get to that, maybe, yeah, I said let's take a quick time out and talk about the chapter problem. You guys read this, right? Now, there's a lot of questions being asked, so I want to highlight some of them. What are we trying to estimate here? Does it say? Yeah, so in the chapter problem, they have this 70%, right? 0.7. 0.70. That is what? It's the proportion that, I like the way you say that, believe in global warming. Okay. So that's what we mean by a proportion. 70%, right? It's a fraction. It's part of what? Okay. I guess my first question to everybody, and I want you to talk to someone near you about this, is would I denote this 70% by P or P hat? Okay, what do we say? What is this? P hat? How many say P hat? That's P hat. Why? It's a sample. How big was the sample? 1,501 people. That's a pretty big sample, right? So now, here are the questions that the chapter problem asks us to think about. If we have an estimate that is 70%, and I just gave you the fact that somehow that's the best point estimate, is to do a sample proportion. That's the best point estimate you can get of a population proportion. Whatever best means. We'll get to that. Okay. How can we use the results of the poll to say what the population proportion is? What's that? It's an estimate. Well, how? And then that leads to the second question. How accurate is that 70% going to be? And then I like the third question. You asked 1,501 people out of 225, what is that? Million adults in the U.S. population. So does this mean anything? Well, don't say no so quickly. Don't say no so quickly. We keep reading this 30, and we might wonder where that's coming from, and I think we're going to answer that very soon about why the book keeps saying 30 for a sample size. Of course, 1,500, that's much bigger than 30. And then, does the method of selecting the people to be polled have much of an effect on the results? Well, how did they select people? Did it say? We know from Chapter 1 that that does make a difference, right? How you select people. What does it say? It says a Pew Research Center poll. I'll tell you what, if they're a research center, I'm going to bet they did their homework and they did it right. They didn't say, hey, anyone that wants to participate, turn it in. It says randomly selected. So I'm sure they did a simple random sample, or at least as best as they could simulated that, right? Okay. But those are the questions that we want to ask today, and as we move through this chapter. How do you use the results of polls? You know, and like I said, this may be very relevant to the kind of stuff you may want to say on your paper. You might say, well, I read a study that says this. Okay, well, what does that really tell us? This is kind of the opposite of a point estimate. It's used to estimate, right? But what you're going to have is you're going to have a range of values. So my confidence interval might be, okay, how about this? I'll say 0.65 is less than P is less than 0.75. This is an example. So what would that say? What would that mean if I say 0.65 is less than P is less than 0.75? What's P stand for again? That's the population proportion, right? This would mean, if I'm still thinking about the chapter problem, this would mean, well, the number of Americans that believe in global warming is between 65% and 75%. Now, can I say that? I don't know. All I know is I have one sample, and the result of the one sample was what? 70%. How about this, guys? Could I say this? So okay, I want to be careful about the language I use. I'll give you what the words are as we get to them. But the ideas are what I'm going across right now. How many think I should be able to say this? 0.55 is less than P is less than 0.95. From what we know now. Well, what about the first one? Yeah, you know, it'd be nice if I could say this, right? But what if my sample was just kind of a bad sample? Now, it's more likely I heard someone say that I could say this. I could definitely say this. Right? I mean, I'm not impressing anyone if I do that, right? But I like how someone said that this is more likely, in a sense, that I can say this. You're giving it more room for error. For error. More room for error. Let me write that down. More room for error. And so, as we move through today's class, we're going to talk about how do you pick a confidence interval. And when I pick an interval, I will also tell you how confident I am that P is in that interval. I am less confident about this. Right? My sample was 70%. Now, actually, I may be fairly confident about that. I don't know. Maybe I have enough info to figure out that it's between 65 and 75, probably, or that it's very likely to be between 0.55 and 0.95, right? But I need more tools, and so I'll give those to you as we move through here. Okay. Yeah. Here's another definition. A confidence level. It's going to be a probability 1 minus alpha. there's that letter alpha again that we saw on the exam, right? It's just a Greek letter A, but it's used quite often. That the confidence interval actually does contain the population parameter, assuming that the estimation process is repeated a large number of times. Most common choices are 90%, 95%, or 99%. See, if I want to be 99% confident that the population parameter is in my interval, that means alpha is 1%, this is going to be a bigger interval. If I'm happy enough just being 95% confident or 90% confident, then you'll have a smaller interval. But this is how these samples are interpreted. When someone does a study and they say, okay, we got a study that says 70%, what they'll report is they'll say, okay, that means the population is between this and this with certain level of confidence, 90%, 95%, 99%. Does that make sense? We're going to see more pictures that are going to help you make sense of this. Yeah, Craig. Yeah.
Whenever you see on SoFA, they always say that they got rid of 99.9. Like, when you're saying, like, that's, like, the most common choice, like, people just put that down?
What I'm saying is that, yeah, when people give you confidence intervals, you know the one I see the most is this. 95%. That's what people usually do. Matter of fact, when our book was talking about, 5% being kind of unlikely, that's kind of the reason, because 95% confidence intervals are used all the time. But sometimes people want more confidence. But if you want more confidence, what's the price you pay? You need a bigger interval. Does that make sense? If I want to be more confident, I can do it, but then I get a bigger interval. But if you say, no, I want a smaller interval, I can do it, but then I'm less confident that the parameter's in there. Does that make sense? Caution. Oh. Yeah, I'd like you to take a moment to look at page 330. This is important. You need to know the correct interpretation of a confidence interval. And you might want to make a little note to yourself to look at page 330 again whenever you're trying the homework. Okay? So let me open up to it. So if you read the correct, suppose your confidence interval was this. They say 0.677 less than p less than 0.723. So they're saying we are 95% confident that P actually lives somewhere in that interval, the true population proportion. Okay, that's what they're saying. This means if you kept doing these samples over and over and over again, meaning what? Survey 1,501 people. Simple random sample. See, the next time I did it, do you think I'd get 70% again? I'd probably get something different. 69% or 74%. I don't know what I'd get. I'd get a different number because it's a different sample. But if you do it over and over and over and over again, what did we learn happens? The sample proportions, if you do it over and over and over again, what kind of distribution do we approach? We approach a normal distribution, right? And it'll be a normal distribution that's centered around the real population P. And because of that, what I can do is I can say, okay, I can be 95% confident that P is between this and this. And how do you do it? let me show you kind of a rough scheme before we actually do the problem. If I want to be 95% confident, what I do is I think about the bell curve, which is going to be what this approaches. And remember I said this is a very important idea, that you're able to think about if this is 0.95, then what am I able to compute using inverse norm? Z-scores. Okay? What would you take the inverse norm of? Inverse norm of what? From that picture, yeah, we need to look at the sides, don't we? We need to look at how much area is right there. So how much area is right there? 2.5%, right? Because there's 5% left over, but we know it's split between both. So that's 0.025. 2.5% is what's left over here. So if I do the inverse norm of 0.025, that'll tell me what that z value is. All right, I can do that. Haven't done that in a while. I told you this was going to keep coming back. Okay, inverse norm. I said that's the most important thing we're going to do in this course is the standard normal distribution stuff. Hey, negative 1.96, right? I think I've seen that number before. Negative 1.96. I think that was on your test. Here's z equals 1.96, just by symmetry if you want. Those are the z-scores. Well, wait a minute. What does that have to do with these numbers here? Well, remember that in addition to having a standard normal distribution, which has z-scores in it, don't you also have a normal distribution over here where you're going to have x, right? And x here might be the population proportion. And it's going to be centered around whatever p is, right? And so then, through a little transformation, you can turn those z-scores into these scores. Now, I'll go through exactly how to do that again. But that's the game plan. Does it make sense? David? Okay. You understand where I got 0.95? How much is left over? 5% left over. 2.5% here. 2.5% there. I always like to work from this side because then I get the z-score right away. Some people work from the right. Kind of depends how you think of it. Oh, I said caution, know the correct interpretation. Look at some of the incorrect interpretations. Is it true that there is a 95% chance that P is here? Not really. P's either there or it's not. It's not, there's a 95% chance that the population parameter moves somewhere. It doesn't move anywhere. The population parameter is there. There's a 95% chance I got it right, that I contained it. Does that make sense to people? And there's one more caution, but it's not yet. We'll do that next. The number z alpha over 2 is a critical value that is a z-score with the property that it separates an area of alpha over 2 in the right tail of the standard normal distribution. Blah. In the last problem we were talking about, the one I was putting up here on the screen, I was imagining 95% confidence, right? And so I drew a picture of the normal distribution like that. And I said that this was the area in here that we wanted, and this was 0.95, 95% of the area. And then what did we compute? Well, this is what you asked me the question about. You said, why did we compute that area to be 0.025? And that's because how much area was left over? Yeah, alpha would be 0.05, 5%. So the reason that they call this thing Z alpha over 2 is because when you do the inverse norm on your calculator, you don't put in 0.05. You put in 0.05 over 2, and you do the inverse norm. Does that make sense to people? That's what I did. And I get a z-score. And that's Z alpha over 2. Now, when I did it, I got the negative z-score, right? They just take away the negative sign, and that's this one. And that's what they're going to call Z alpha over 2. So in the last example, our Z alpha over 2 would have been 1.96. So I think this was worth doing, not because I like the words, but I do think the idea is important, and now maybe you can understand when you read. That's okay? It's a lot. There's a lot going on. We're at 11 o'clock. Why don't we take our break? I showed you this picture. I basically drew it, right? You asked me, why was it alpha over 2? Well, because alpha, right, that's how, what's the chances that I missed with my net? And if we know we have a normal distribution, and I want 95% confidence, that's this blue, well, then the other 5% you split up here and here. That's why we did alpha over 2 for the Z value. These pictures are all in your book, too. Yeah, here's the picture we just did, right? We got 1.96. I like this. It's kind of nice. Ah, those are called critical values. I didn't make this slide, but I like them. They're pretty. How do we find Z alpha over 2 if you want a 95% confidence interval? You know, wasn't this your last question on that exam I just passed back? Wasn't it? It must have been an important question. Yeah, so, you know, 95% is what we want, so alpha is 0.05. Now, their suggestion is take the 95, add on the 0.025, and then, you know, split it up. I think it's easier to look at this one, because then you can go right to the table or right to the calculator. Find the negative one first, and then you know that this one will be the same but positive. So yeah, the Z alpha over 2 plus or minus 1.96. Okay, new definition. How many have heard of this expression before? Margin of error. All right. Margin of error, denoted by E, is the maximum likely difference with probability 1 minus alpha, such as 0.95 between the observed. You don't write that down. Don't write that down. That's awful. I mean, that's too hard. What are they doing? They're measuring between P hat and P. Right? And then there's this word in here, difference. What's a difference? We're going to subtract. The maximum likely difference. Okay. Let's see how this works. Oh, there's a formula. The margin of error for proportions. E equals Z alpha over 2 square root. What the heck are we doing here? You know what I want to do? I want to try and compute this, but then I want to try and make sense of it. Because we can all use formulas, but they have to mean something. So in our example, the margin of error equals, you guys, what was Z alpha over 2? Wasn't that the Z value that I found? And wasn't that 1.96? right? I guess it was plus or minus that. 1.96 times the square root, okay, of, now what is p hat? So in our example, what was it? Wasn't it 70%? That was the study we were looking at in the chapter problem. P hat was 70%. Now I found this kind of amusing. They write down Q hat in the formula, and I couldn't find anywhere in the book that they tell you where that is. But I bet you know what it is. It's going to be 30%. It's the same notation we used when we did binomial distribution. You have success and you have failure, right? And you divide by n. Do you remember what n was for this study? 1501. Oh, okay. Actually, remember we said you only need 30 to be able to do something or other? To get a good study? To start getting the bell curve? Sample size. We said n greater than 30 is what you needed if you wanted to be approximately normal. Then you might argue, why would they contact 1,500 people if all they need is 30? Here's your answer. Notice that the large sample size reduces what is called your margin of error. For a proportion. Okay? So let's see how this works. Plus or minus, I guess I want to compute that. All right, let me get a calculator up here. So I have, oh, there we go, 1.96. So times, I want the square root of 0.7 times 0.3 divided by 1501. Okay, so my margin of error is plus or minus 0.023. But what's that mean? That's our question. We'll see that shortly. Jim? Is going to be p hat minus the margin of error is less than p hat plus the margin of error. What was our margin of error again? I want to go back to the last slide. 0.023. Okay. So where it says E, I'm going to go ahead and write 0.023. Right? Okay. Here's P. What was alpha in this example? Yeah, that was my 5%. So this was for a 95% confidence interval, right? If you want a 95% confidence interval, it will look like this. P hat minus E is less than P hat plus E. Now, I used this formula already, and I computed 0.023. I did that on the last slide, right? Notice, you better know your 5%. You better know what alpha is, right? Or at least you have to know the z value. So you got to know how to do the stuff in Chapter 6, or else no chance. Okay, what was our p hat from our example? 70%, right? So what we're saying is, this is what I want. So let's see. 70% minus 0.023. Let me compute that. Okay. 7 minus 0.023. So 0.7 minus 0.023. Oh, okay. 0.677. is less than P, and that's less than 0.723, this is what you call the 95% confidence interval. Does that make sense? Isn't that exactly the interval we had in that exercise? Which problem did we do? I'm not taking notes. Let me go back. What was that problem we did? Wow, it was like 10 slides ago. I'm recording this? This is ridiculous. Page, yeah, there's that. Where was it? Page 330 we did one. Oh yeah, page 330. There it is. How about that? Well, now you know how they get it. So what are the steps? Let's go through it one more time. Because this is what you're going to have to do for homework. They're long processes, right? I'm going to say construct a confidence interval. I have to tell you what kind of confidence interval. In this example, it was 95%, right? What if I told you 90%? Then what would that mean alpha is? Alpha would be 10%, right? So you'd take alpha, which is 10%, and split it up into two tails, which is 5% each, right? And then you'd find the z-score that would go with that 5%. Now the z-score that went with our 2.5% was this. That's z alpha over 2. Who's with me so far? Yeah. That's all this is. This is one big fancy name for 1.96. Now why do they call it z alpha over 2? Because alpha was 5%, right? But you don't want the z-score of 5%. You want the z-score of 0.025. They want to remind you of that by saying, look, don't do alpha, do alpha over 2. It's a reminder. Times this square root. That's right. Okay, Sonia? Yeah, they'll tell you the sample proportion. I needed to know that.
Yeah, because you said the 90, if we did the 90% confidence.
Then this would still be 70. Yeah. Kate?
So do you always have a positive negatives because you have the positive negative z-score, or is it
Yes.
square root?
No, because of the z-scores. Square roots are always positive, turns out, the way that they're defined. Now, after we got that z-score, and then we filled in the rest of this, we had E, margin of error. What do you do with margin of error? You create your confidence interval with the margin of error. See? I took my 70%, my point estimate, and I subtracted the margin of error, and then I added the margin of error, and now I got my confidence interval. This is the 95% confidence interval for the proportion. So you need to compute E so you know what to add and subtract from your point estimate. And even when I do that, I'm still not guaranteed that I caught my parameter. I'm not guaranteed. What's the chances that I caught the parameter? 95%. If I want to be more confident that I caught it, I'm going to need to make a bigger net. So I could be 99%, but then I'll have a bigger range. And sometimes that's not good. And sometimes that is good. You kind of have to pay the price. Okay. We have to find the error. I'm going to write a formula up on the screen for you again, just to remind you. I don't know how good you're going to remember these formulas. But you'll have a formula page, of course, you know, always in your book. Hang on one sec. I want to write the formula up here. So according to our book, the margin of error we're looking for eventually is 0.0186. I'll see if I get that. 0.0186. 0.86. That's what they say. Now let's see. Z alpha over 2. Okay. Z what? Do we know what alpha is? What is it? Because they say I want 90% confidence. So alpha is what? 10%. So I want 5%. I want Z of 5%, right? And then I'm going to do square root. Now, do they tell me what my sample proportion was? Oh, boy, let's see. The sample size is 1780. Oh, 35% success. So that's going to be 30.35. And therefore, Q is 1 minus that, which is 0.65. And I had 1780 for my sample size.
Did you say 0.65 because that's the opposite of 0.35 to get 1?
It's 1 minus that. That's right. P and Q have to add up to 1. Hang on one sec. Julie, question. Yeah, someone else just asked that. Basically, Q is always 1 minus P. Okay? P plus Q has to add up to 1. So since they told me 35% was success, then Q, which is the population of probability, the probability of failure would have to be 65%. Is that okay? P was 35. They gave that to me. 35%, I should say. 0.35. Yeah. All right, let me work through the calculation and see what happens. First, I'm going to do the z-score for 0.05. All right, let me do that. So what do? I want the inverse norm. So let's see, where am I going to go? Thank you. Second, bars. Distribution. Inverse norm, because I want a z-score of 0.05. And I could draw the picture again, but you guys get it, I think. So that's my z-score, right? Plus or minus that are the two z-scores. And now I want to multiply by, well, the square root of, maybe I should slow down. Well, it's all right. This is how I would do it. 0.35, right? That's my p-hat. Times what? 0.65 divided by 1780. And then I'll close the parentheses. And you notice these parentheses are after the square root. It's going to take the square root of all that stuff first and then multiply it by the answer. And it gives me negative 0.0186 if I round, which is what they got there.
So should we not round them just to make the margin of error more accurate? Like, should we not round the z-scores?
Oh, yeah. The less you round, the better off you are.
Round at the very end.
Rounding at the end is the best. That goes for any math class or science class. If you round later, you're better off. Okay. Yeah, I guess if you rounded this z-score to, say, 1.64, you'd be losing a lot of digits that were significant, I guess. Cool. All right. I guess it'd be positive. The error is positive. Okay. Well, okay, now that's a good question. Kate's like, we're not done. See, all they asked me to do was compute E, right? Now, later in the section, they're going to say, find the 90% confidence interval. So what would it be? What would be the 90% confidence interval? Yeah. You could write it as 0.35 minus that number, comma, 0.35 plus that number. There's my confidence interval. It goes from whatever that is to whatever that is. They didn't ask for that, but that's what you would do. Okay? Now, I deliberately picked out one more here, problem 36, and I think there was a reason. Oh, global warming. Well, yeah, so do I need that? Yeah, we can talk about this one, I guess. It's the same poll. I guess I want to at least answer part A, and then I'll skip the rest, I think, because the rest is very similar. What is the best estimate of the percentage of adults who believe that immediate government action is required? Okay, so this is a different question. Do you think immediate government action is required for global warming? Well, they did a study. How many people were surveyed? 1708. How many said yes, take immediate action? So I guess my question is, what's p hat? Yeah, here, no, p hat is 939 out of 1708. I think that's more than 50%, right? 55%? Okay, so it's 55%. I guess my point is, they don't have to give me p hat. Sometimes I have to actually compute it, right? What proportion was it? Okay, well, it's 55% if I round. Okay? And then everything else would be the same. Part B, they want you to do a confidence interval. I think it was 99%. That's enough for this one. Sample size. I want to talk about sample size a little bit today. Suppose we want to collect sample data in order to estimate some population proportion. The question is, how many sample items must be obtained? Now here's the deal. We already have a formula with sample size in it. Do you know which formula it is? Which formula did I give you guys that has sample size in it? E. I'm going to go through this very quickly, the next few steps. If I want to know the sample size, what you'd want to do, I guess, is get the sample size by itself from an algebra standpoint. So I could do something like E divided by the z-score is the square root of p q over n. And I know these are hats. And then do you know what you'd have to do to both sides? If I'm trying to get the n by itself and I have this big nasty square root here, you have to square both sides. You have to square both sides. That's how you undo square roots, is you square both sides, okay? Now this class is not an algebra class, okay? I'm not going to go crazy here. I will show you where this formula comes from and then just kind of leave it at that. So now we have p hat q hat over n. And then the next thing you might do is you say, okay, I'm going to flip both sides. Take the reciprocal on both sides. And then for a final step, I'm going to multiply both sides by p hat q hat so that it'll cancel and give me just n over here. Now your book doesn't really show all this, but they end up with this as a formula for sample size. P hat q hat, z alpha over 2 being squared, divided by E squared. And I think that's here. Well, that was the old formula. They say, do some algebra and get this. Sure. But I guess what you need to know is that if you do some algebra, this is the formula you want. Okay? Real quickly. Going back. Okay. And this is all in the book, of course. I mean, we have a formula for sample size. It makes sense we'd have one because we already had a formula with sample size in it. It's just a matter of getting the n by itself. So now, what can you do with this? For example, problem 44 is worth reading. I'll leave this up. But problem 44 is worth reading. This is on page 343, problem 44. Remember Rudy? Rudy Giuliani? How many recognize that name when I say that? Rudy Giuliani?
I recognize it.
See, if you want to run for office, you better have a name that people recognize. You know, we have issues 5 and 6 in Cuyahoga County, where I live. I don't know if any of you have heard some of the press about it, but, you know, people are running for these offices, and, you know, there are certain names that always get elected. There have been people that have legally changed their last name to a name that is popular in the government, and then they get elected. Because someone looks at the ballot, and they see that name, they say, oh yeah, I know that name. Check. I don't want to point out any names. But I just want to say it's done. So they wanted to know, in problem 44, hey, Giuliani, do you recognize that name? Well, it says here, we want to be 95% confident that we know what the percentage of U.S. adults will recognize that name. Okay? So we're going to construct a confidence interval. And it says here, a recent survey indicated that Giuliani's name is recognized by 10% of all adults. Now, we did better than that in this class. Okay? But if 10% of all adults recognize that name, okay, what's that 10% going to be? That's the p-hat. That's going to be 10% for us. Okay? So what else? Q-hat is going to be 0.9. Z alpha over 2, well, wait a minute. What do we want to put in there? They want a 95% confidence interval. Hey, wait a minute. We already did a 95% confidence interval. You know what we're going to square? We're going to square 1.96. Right? How many remember that number, 1.96? It keeps coming back. Because this is the z-score that goes with 95% confidence interval. So it's going to come back a lot. And then we'll just have to divide by e squared. What's e? Do we know? Oh, wait, it says you want to be 95% confident that the sample percentage is in error by no more than 2 percentage points. Do you see in the text where it says no more than 2 percentage points? Who sees that? Oh, man. Then you're going to have trouble finding E. Do you see where it says that? That's the kind of thing you have to do here is find E. So E here is going to be, well, 0.02. So I would divide by 0.02 squared. And that'll tell me the sample size that I need for this problem.
How did you get it?
The formula. How'd I get what? E? Read in the text it says we want to be 95% confident that the error is no more than 2 percentage points. Do you see it in the problem? You have to look at the book. I think that's the hard part, is not the formula. The formula is easy. The hard part is finding the stuff in the text, and that's why I wanted to show you an example like that. But then you plug all that in, and if we work it all out, the sample size you would need here is 865. Okay? That's right. You would have to survey 865 people. So we did problem 44. It says, caution, never follow the common misconception that poll results are unreliable if the sample size is a small percentage of the population. See, here's the other big caution. You can still have a good survey. It's just that you won't get as small of a confidence interval. But you can still get a confidence interval even from a small survey. So that's important to understand. Yeah, I'm done with this because of time. I would love to have your homework on the way out, absolutely. Tell you what I'm going to do for Thursday. Well, I may make an update to the schedule, that's all. Just leave it at that, okay? But you definitely have what you need to do section 8.2. I'm sure of that. I have to decide what I'm going to do with 8.3. But because we haven't talked about it at all yet. So I'll see. But definitely do at least 8.2. Okay? What is that?